Hello, ladies and gentlemen. Thank you for attending our presentation today. It will be about 8 to 10 minutes. Our team consists of Devin Ayotte, Damien Badical, myself, Jackson Koch, and Robin Reed. We'll be going through our autonomous guided vehicle MET automation capstone. Thank you to our client, Christopher Dick, our technical advisor, Daniel Barrett, and our communications advisor, Joan Magnuson. On the left, you can see we're working with a Robotino 3, which is an educational and research-oriented robot made by Festo Didactic. Next slide, please. Today we will be going over our problem statement, the scope of our project, as well as the constraints and limitations, a functional analysis, the research we did, and the morphological charts we made, the conclusion, and then you can ask us some questions. Next slide, please. So we were tasked with further developing, configuring, and programming of an autonomous guided vehicle to function in the State Mechatronics Lab, that being the Robotino 3. In the bottom right, you can see a picture of the Mechatronics Lab. Next slide, please. So the main goal of our project is the transfer of parts and materials between robotic arm work cells in the Mechatronics Lab. We also need to create sufficient documentation to ensure instructors and future students can add on to our project. So design of a gripper and a storage plate is necessary to pick and drop off parts. And in any project, safety is the biggest concern. The Robotino will be functioning around people. Finally, we need the Robotino to charge itself. At the right, you can see a picture of one of the robotic arm work cells in the Mechatronics Lab. Next slide, please. So again, safety is of a huge importance when considering constraints and limitations. We don't want the Robotino to injure anyone working around it. Reliable obstacle recognition and avoidance is necessary so that the Robotino can autonomously navigate and safely when it's going around people. Implemented functionality cannot interfere with current functionality. And just for example, is the gripper we are designing cannot interfere with the current gripper on the Robotino. And then finally, one of the biggest constraints is COVID-19. We have limited access to the lab and each other. At the top right, you can see a picture of the input-output interface on the Robotino. And in the bottom right, you can see a representation of how the Robotino sees the world. I will now hand the presentation off to Devin Ayotte.
Thank you, Jackson. So what we're looking at here is a functional analysis of the process that we're going to implement. If I can draw your attention to the top left, we can follow the red arrows throughout the process here. First, the ABB robot signals to the Robotino that a part is on the conveyor and ready for pickup. And if we follow the red arrow to the right, this pickup is added to a queue. The Robotino then verifies that it has sufficient charge to execute the movement and then checks that the sending and receiving work cells are ready for it to safely enter. It travels to the first work cell, checks once more that it is safe to enter and then collects the part, and then travels to the second work cell, checks once more that it is safe to enter and deposits the part. At this point, it checks to see if there's another pickup in the queue and repeats this procedure if there is sufficient charge. If there's no pickup in the queue or if the charge is insufficient, it will return to the charger. So we spent a decent amount of time investigating the best way to implement this, and we began by looking at other educational robot platforms such as the Turtlebot, which we see here. It's quite similar to the Robotino in terms of its purpose, applications, and capabilities. And our further preliminary research focused on three main points, those being the programming environment, the sensors and navigation methodologies, and the gripper that we'll use to handle and transport the parts. So I'll begin here by discussing the programming environment, and then Robin will discuss sensors and navigation. So our needs for a programming environment were very straightforward. We need an environment that is adaptable, scalable, and relevant in industry while being attainable in under a semester. So we settled on ROS, or Robot Operating System. It is middleware, which interfaces between software and hardware, which is well documented and widely used in industry, as well as being very adaptable. Next, we had to choose the best way to interface between the Robotino and the ABB robot controller, and we've used sockets, socket programming functionality that was built into the ABB to communicate with ROS on the Robotino from the ABB controller. And this then steered us into ROS's node-based system, in which we use Python to control synchronous and asynchronous data streams between different parts of our project. And this also made it much easier to collaborate by breaking tasks into smaller parts. And finally, we needed to choose how to distribute a fairly intensive computing workload. We have thus far used an external computer in the mechatronics lab to help with processing data. Processing data from our sensors and navigation software can be quite intensive, and Robin will now walk us through that.
Thank you. So our team did some significant in-depth research into the ideal sensors to use for the scope of our project. The figure on the top right here shows the pre-installed infrared sensors on our Robotino. They're the little black squares you can see. And to the left, we have a figure showing how they are mapped out and installed in our Robotino. On the bottom right is a figure of a Kinect, which is the depth camera we are using. Next slide, please. We had three categories to go through in regards to sensors and navigation. For our obstacle detection, we chose to use the Kinect that you saw in the previous slide, as well as the pre-installed infrared sensors. They are used for determining the distance from the Robotino to the target. By using the Kinect alongside the infrared sensors, we are able to cover close and long-range obstacles, leaving the Robotino with virtually no blind spots. Additionally, we are using the bumper at the base of the Robotino, which is being used as an emergency stop if the Robotino were to come into contact with an obstacle. For our navigation, we have mapped out the environment of the lab and will be using automatic navigation to determine the easiest path to any given coordinates. Automatic navigation allows the Robotino to self-correct and problem solve while moving, so it can be more accommodating of unmapped or moving obstacles in the lab. In the next slide, we have a map of the lab or the environment that our Robotino will be working in. This map was generated by our point cloud, which was converted to a laser scan. And the map was then generated by taking the closest point that the Kinect viewed and defining that as an obstacle. As you can see, we have 4 blue blocks there. Those are our robot work cells that the Robotino will be traveling in between. And the red blocks are unmovable obstacles or the more static obstacles in the environment that the Robotino will work to avoid. To the left, we have a green block, which shows the Robotino docking station where the Robotino will be charged. We will move to Damien next with the gripper.
Thank you, Robin. So to get a better understanding of what exactly we're moving in the lab, here we have a figure showing the storage tray that we're going to move from one conveyor to a different one in a different work cell. As you can see, there are literally no features that we can hold on to lift the tray off the surface, because all the holes you see on the surface are reserved for storage of an object on top of it. It is also made out of aluminum, therefore we cannot use magnets. Knowing this and knowing that we have to slide the plate off the surface or the conveyor, we did our preliminary research on the next slide and found 2 different solutions. Those are, for ones on the left side, in VIA robotics, where the robot uses vacuum grippers to grab an object and slide it or pull it off the surface. On the right side, you see 2 figures showing off the Conveco solution, where a cascading arm is passing the object, extending barriers in the back, and pulling the object off the shelf. Equipped with that research and that knowledge, and knowing that there are different heights, or that the conveyors are on different heights in the work cells, we see on the next slide our morph chart for the gripper. Basically, what we chose to do is, on the left side, you see the functions. On the right side are the solutions for each function. So we chose to go with a lead screw guided by steel rods. And for simplicity, we chose not to use any extension of the gripper itself. We will drive onto the conveyor, or right next to the conveyor, so that this is not necessary. And then we will use a lock and pull mechanism by using a C-shaped gripper, and for support during driving, we will be using arms that can move away. Since that is probably pretty tough to visualize, we now see on the next slide a current solution. On the left side, you see the gripper with all the parts, and on the right side, you see how it would go next to the conveyor, the arms spread apart. It would grab the work tray back up, and because on the arms there are torsional springs, the arms would come back out and immediately support the work object. In conclusion, our problem or our task that we were given is to move the work trays in between the work cells using a Robottino safe by avoiding static and dynamic obstacles. We chose ROS because it's adaptable, open source, and there is great documentation available. We're using a Kinect depth camera, infrared sensors that already exist, a bumper for emergency stops, and we showed off our initial gripper concept. I'm sure you have lots of questions, and we are happy to answer them right now. If there are no questions, we would be very interested if anybody else has done a similar project where a vehicle was guiding itself or navigating through a dynamic environment.
I have a couple questions relating to the project. One being, how do you guys plan to keep this project on schedule? Like, this seems to be a very programming heavy, very labor intensive project. So how are you going to have this done by April?
That's a very good question. And so what we've done is we split up the project in smaller parts and distributed them. And we also determined what has to be done first. And once one step is done, we're moving on to the next one. We're keeping track on, for that, using a Gantt chart that is usually always up to date. And maybe Robin wants to speak to that a little more.
Of course, yeah. We started our Gantt chart at the beginning of the semester when the project began, and it's been very dynamic, continuously updating throughout the project as our progress is being made and as new tasks and new challenges come up within our project. It's been we've been able to stay on track so far, and we're seeing the next steps in our project and kind of the final outcomes we want to see as we are going forward. It's been good. Thank you.
Awesome. Other just side comment off of that, I want to say very nice CAD models. I was not expecting to see that in-depth of models this early on in a project. So kudos to you guys.
Thank you. We appreciate that. Any further questions? Okay, well, that was it from our part. We appreciate that you were part of that presentation, and we'll hand it back to Chris.